Welcome back to our deep dive series on ISO 26262. In our previous discussions, we've covered parts 1 through 6, looking at management, concept, and development. Today, we're moving into a really critical area, part 7. This one's all about what happens after a vehicle is designed and developed. We're talking production, operations, service, and decommissioning. It sounds maybe less glamorous than design, but it's absolutely vital for keeping you safe throughout the car's entire life.
It really is. The main goal of Part 7 is, well, to make sure all those functional safety requirements we designed in earlier, they actually stick. They're maintained right through the entire post-development lifecycle. It's all about managing risks that could pop up later. And, the key thing here is maintaining the A-cell integrity, that safety level we assigned, even after the car leaves the factory, the start of production.
No.
So today, we'll break down those 4 big phases: production, operations, service, and finally, decommissioning.
Okay, so our mission for you, the listener, is to kind of shortcut your way through this complex standard. We want to unpack how safety is really maintained long after the factory floor. We'll highlight some maybe surprising details and what it means for you, whether you're driving the car or working on it. Let's dive in. All right, first stop. The production line. The car's designed, safety concepts are approved. Now, how do you make sure that safety isn't just theoretical, but it's actually built into every single vehicle consistently? I mean, just imagine the complexity. Manufacturing thousands of safety critical parts. How is that precision guaranteed every time?
Yeah, that's the heart of the production phase challenge. You've got to preserve the safety achieved during development and make that transition from design drawings to, actual cars rolling off the line. It's about making sure design safely becomes produced safely. A big piece of this puzzle involves process capability and control plans. Basically, you need proof that your manufacturing processes can consistently hit the targets for what we call safety-related special characteristics, or SRSCH. Think about the exact torque on a critical bolt, or the precise voltage calibration for a sensor. We use statistical methods like capability studies, CP maybe, to show the process is stable and capable. And it's not just machines. People need regular audits too. Then the control plan details everything: inspection methods, how verification happens, the pass-fail criteria, what to do if something's wrong, and it's all scaled to the A-cell.
Stricter controls, right? Like way more checks.
Exactly. More stringent controls, more frequent checks, tighter tolerances. It's absolutely A-cell appropriate.
It's kind of like building a simple garden shed versus constructing a skyscraper, maybe. The skyscraper demands obsessive attention to every weld, every bolt, every single step.
That's a good analogy. And just like with that skyscraper, you need records. That brings us to traceability of production data. Every safety-related item or element needs a unique ID. Could be a part number, serial number, batch number, even tied to the VIN. And this traceability needs to link back to how it was made, the production parameters, test results like from end-of-line testing, calibration data, and its exact configuration, like the specific software and hardware version.
Wow. Okay. So theoretically, you could trace a specific sensor in my car right back to the machine that calibrated it and the software version it was running when it left the factory. That's intense.
It is intense. And that level of detail is crucial if something ever does go wrong later. But traceability alone isn't enough. You need the human element sorted. That means clear work instructions and training. People working on safety-related stuff need specific training. Things like handling high-voltage components safely, using ESD protection for sensitive electronics, understanding critical assembly tolerances. Instructions need to be super clear, often visual and controlled. And the golden rule: only trained and qualified people touch safety-affecting operations.
Okay, so train people, clear instructions, traceability. What else? How do you check? It all came together, right?
Right, that's verification of correct item integration. Checking that the right hardware is talking to the right software, components are installed correctly, torque's right, alignment's right. Any slip up here has to be caught and fixed before the car moves on.
Oh.
Which leads naturally to end-of-line EOL testing. This is mandatory for A-cell items. It is the final check to confirm everything works as intended, safety mechanisms function, calibration is correct, it communicates properly on the vehicle network, and guess what?
The results get stored and linked to that traceable ID.
You got it. All stored and linked. And sometimes, especially for really high A-cell stuff like A-cell D, you might even do fault injection testing. It's usually optional, but recommended.
Right.
You basically deliberately introduce simulate a sensor failure to make sure the safety mechanism kicks in correctly, like the ECU going into a safe state.
Okay, let's just unpack that for a second. The level of detail here is incredible. From a tiny solder joint specification to tracking software versions, to deliberately breaking things just to test the fix, all so you can trust the car you drive off the lot. It's a hidden world of safety engineering.
It truly is. Now let's shift gears. The car is off the lot. It's built safely, tested thoroughly, and now it's out there, maybe even in your driveway. What happens next? This is the operation phase. The goal here is to keep it safe during its intended use, spot any systematic problems that maybe didn't show up in testing, and make sure any updates or changes in the field don't break the safety. It's like the car enters this continuous monitoring state. We need monitoring of field incidents and failures. We're actively looking for new hazards or maybe failure modes we didn't anticipate. How? By collecting and reviewing reports from dealerships, maybe customer complaints, warranty claims data. We also track diagnostic trouble codes, those DTCs that pop up during service. And we look at parts that get returned, especially if they're marked no trouble found. That can be a clue. If something looks serious, especially if it's safety related, it triggers a root cause analysis and gets escalated.
So the car is constantly feeding data back in a way, even just through warranty claims and service visits. What kind of data specifically helps update the safety picture?
Yeah, it's a constant flow. We rely on collection of operational data. Sources include warranty claims, service logs, those DTCs, customer feedback directly, and increasingly, telematics data streamed from the vehicle itself. And we don't just collect it, we analyze it, looking for trends, comparing actual field failure rates to what we predicted in the safety analysis, like the FMETA. If reality differs significantly, we might need to update the risk assessment. This also helps with field monitoring for systematic failures. These are the tricky ones. Latent software bugs that only show up under rare conditions, or hardware aging effects like tiny cracks in solder joints or sensor drift over time. Field return analysis and setting up early warning systems help catch these.
Okay, that makes sense for catching problems. But what about helping the driver use the car safely in the first place and keeping them informed?
Absolutely critical. That falls under customer information. Manufacturers have to provide clear, easy to understand operating instructions. Think user manuals, quick guides, labels right there on the vehicle. This covers everything from how to plug in your EV charger correctly to maintenance schedules to what to do in an emergency. And just as important are the warnings and limitations for safety systems. You see them all the time. Driver assistance is not a substitute for driver attention, or maybe temperature limits for charging. These are mandatory for ASAL-related functions, often using standardized symbols, to manage any remaining risk.
Right, the fine print. That's actually really important, fine print. What about changes after the car is sold, like software updates? That seems like a big area for potential issues.
Well, it's huge and heavily regulated within Part 7. That's field updates. Whether it's an over-the-air OTA update or one done at the workshop, the implementation has to be safe. That means secure flashing mechanisms, authentication, signature verification to prevent malicious code, making sure the correct version is installed, and doing a post-update verification, like a quick system check or checksum validation. And here's a really crucial bit. There must be a rollback strategy. A plan B to revert to the last known good, safe software version if the update fails or causes problems.
Safety net for the software. Makes sense.
Exactly. And tied closely to that is configuration management in the field. You need a database that tracks everything for each specific vehicle, by VIN usually, which ECUs it have, their part numbers, the exact software versions, calibration settings, and a history of all updates applied. This ensures only approved, tested configurations are actually running in the car, and every single change is documented following the rules in ISO 26262 Part 8, which covers supporting processes like configuration management. What's really fascinating here is how the vehicle and the whole ecosystem around it keeps learning and adapting its safety profile. It's not static. It evolves based on real-world data and controlled updates.
Okay, so production is tight, operation is monitored and managed, but cars need maintenance. What happens when your car goes in for a service or repair? How do mechanics avoid accidentally messing up all this carefully built-in safety?
That's where the service phase comes in, and the objective is crystal clear. Make sure that maintenance, repairs, even reprogramming don't compromise functional safety. You have to preserve that ASAL integrity. It starts, maybe unsurprisingly, with the documentation, the development of service manuals and procedures. And these aren't your simple weekend mechanic guides. They are incredibly detailed. Step-by-step instructions for repairing safety-related components. Think brake-by-wire systems, airbag controllers, EV battery packs. They specify special tools needed, like for HV isolation or ESD protection, exact torque values for bolts, critical warnings like always depowering the HV system first, and specific verification steps after the repair. And importantly, these procedures have to align back to the vehicle's functional safety concept. They clearly flag safety critical steps.
So the technician needs to know not just how to replace the part, but why certain steps are critical for safety. It sounds like they need serious training.
They absolutely do. Training for service personnel is mandatory for anyone working on safety-related systems. Topics cover things like high voltage awareness, safety powering, proper PPE, even first aid. How to correctly use diagnostic and calibration tools so you don't accidentally bypass the safety feature. Understanding the ACL critical functions, how to handle pyrotechnics safely, and records are kept certifications, requalification to ensure skills stay current.
Okay, train tech, good manual, they replace the part. Then what? Just bolt it up and send the customer away.
Definitely not. There's verification after repair replacement, which is essentially a safety validation step. You have to confirm the new part works correctly within the system. This might involve specific functional tests, running onboard self-diagnostics, maybe even checks similar to the end-of-line tests at the factory. The goal is to ensure the repair was successful and didn't introduce any new problems, like new DTCs related to the safety function.
That makes sense. You fix one thing, you don't want to break another, especially if it's safety related. What about software? Do parts need coding?
Very often, yes. Calibration or coding of replaced ECU's components is common. A new ECU might need specific parameters coded in, calibration data downloaded, or it might need to be synchronized with other ECUs on the car's network. And getting this wrong can be dangerous. Imagine coding the wrong wheel size that could mess up speed calculations, ABS, stability control. So this has to be done using controlled official software and configuration management tools provided by the manufacturer to ensure the right software and calibration is loaded.
And I guess the diagnostic tools themselves need controls, so you can't just bypass safety features easily.
Exactly. That's controlled use of diagnostic services, VDS. These services, usually based on the ISO 14229 standard, allow deep access to vehicle systems. Access for things like programming or running safety-critical routines must be protected, often requiring security credentials. Critically, these tools should not allow permanent deactivation of safety mechanisms. And any use of a diagnostic service that changes the system state needs to be logged. OEMs provide tools that enforce these rules and keep audit trails.
This is where it gets really interesting for me. The hidden complexity behind what seems like a simple repair. It's not just swapping parts. It's this intricate dance of hardware, software procedures, and verification, all to keep you safe.
And it forms a loop. There's a feedback loop from service back to engineering. Data from service centers, warranty claims, common repairs, diagnostic logs showing recurring DTCs gets fed back into the overall safety process. This might trigger updates to the original hazard analysis and risk assessment, HARA, or other safety analyses if new failure modes are discovered in the field. It could lead to design changes or even updates to the production control plans. It drives failure analysis and continuous improvement. Root cause analysis on field failures leads to corrective and preventative actions, maybe a service bulletin, updated repair instructions, or a design tweak for future models. Lessons learned get shared.
So even fixing cars helps make future cars safer. That's a neat cycle. Okay, we've built it, driven it, fixed it. What about the very end? The junkyard.
Right, the final chapter, decommissioning. Often overlooked, but still covered by Part 7. The objective here is basically, make sure the vehicle doesn't pose any safety risks while it's being taken apart, scrapped, recycled, or disposed of, especially with things like high voltage systems and hazardous materials. First step is safety activation. Before you start dismantling, you need to disable safety-related functions that could cause harm. That means properly deactivating pyrotechnic devices, airbags, pretensioners usually using specific manufacturer tools or diagnostic routines. You also want to disable things like autonomous driving features so the car doesn't try to drive itself onto the shredder.
Yeah, good point. Avoid any pristine moments at the scrapyard. What's the big safety concern with decommissioning modern cars, especially EVs?
Without a doubt, it's the high-voltage battery disconnection safe discharge. This is critical. OEMs have very specific procedures. It involves isolating the main traction battery, often physically disconnecting service plugs, and ensuring any stored energy in capacitors is safely discharged. Technicians must verify there's zero voltage using properly rated HV measuring tools before touching any HV components. And then the battery itself needs careful handling, storage, and transport according to standards like UN 38.3.
Okay, HV battery handled safely. What other hazards are there?
There's the broader handling of hazardous materials. Lithium-ion batteries need trained personnel and certified containers to prevent shorts or fires. Those pyrotechnic devices need disposal at certified facilities. And you have fluids and gases, coolants, refrigerants, oils that need proper draining and recycling according to environmental regulations. This all ties into compliance with legal requirements. Things like the end-of-life vehicles, ELV, directive in Europe, specific rules for battery waste, international shipping laws for hazardous goods. You need documentation to prove compliance.
So even sending a car to the scrapyard is a highly engineered safety process. It's not just about crushing metal. It's about protecting people and the environment right to the very end.
Exactly. And believe it or not, there's even feedback to development from this phase. Analyzing vehicles at end of life can reveal things like long-term corrosion patterns, how batteries actually degraded over 15 years, or components that were difficult to dismantle safely. These insights feed back to designers to help improve next-gen vehicles, make them easier to service, safer to recycle. Sometimes findings might even be shared with regulators if systemic issues are found. So you can really see how Part 7 weaves everything together. It connects back to Part 2 for management, relies on the safety goals from Part 3, implements requirements developed in Parts 4, 5, and 6, uses supporting processes from Part 8 like configuration management, and is guided by the ASIL analysis from Part 9. Functional safety under ISO 26262 is genuinely a life cycle spanning effort, maintaining that ASIL integrity is the thread that runs through it all.
It really drives home that holistic view, doesn't it? Safety isn't just a design feature you check off a list. It's this living, breathing aspect of the vehicle's entire existence, managed from cradle to grave or maybe drawing board to jump yard. It's quite an undertaking when you think about it. So we've journeyed through ISO 26262, Part 7 production, operation, service, even decommissioning. It's amazing how many critical processes are working, often silently, behind the scenes to protect you every single day you interact with your vehicle. It's a huge testament to the engineering discipline involved.
Absolutely. And reflecting on all this, it really raises a provocative thought for the future, doesn't it?
Yeah.
As vehicles get exponentially more complex, more connected, more automated, maybe even fully autonomous, what new challenges will emerge for operational safety, for service, for end of life? What new dimensions will we need to consider? And how will standards like ISO 26262 need to keep evolving to address them?
That is a great question to leave our listeners with, something to definitely ponder as the technology races ahead. Thank you for joining us on this deep dive. Stay curious and keep thinking about those unseen layers of safety all around us.